Have you ever done a color blindness test and wondered if other people see the same color that you do? In Namibia, there's a tribe that doesn't have a word that differentiates between the blue and green. So, what we see for color has a lot more to do than just what enters our eyes. Today, we're going to look at the photoreception capabilities of our eye, or how our eyes see. So the innermost layer of the eye, we said, is the retina, and it has 4 different layers of cells. It has a pigmented epithelium, light-sensitive cells, so those rods and cones, bipolar cells, sending information from the rods and cones to the optic nerve cells, and then the cells of the optic nerve. That pigmented epithelium is positioned between the choroid layer and the light-sensitive cells, and it has granules that prevent light from entering, light that enters the eye from being scattered, and then it would just kind of bounce around our eye, and we would see a hodgepodge mess of things. So this is really a really important layer. And other mammals, such as cows and cats, that have eyes that function slightly differently, so like cats are active at night, they'll have another layer in their eye that helps them gather more light at night. There's 2 types of light-sensitive cones and light-sensitive cells known as the rods and cones. The rods respond best to low-intensity light, and we use them a lot for our peripheral vision. And then the cones require high-intensity light. They identify color, and we use them for more detailed vision, but they're both sensory receptors. Once excited, the rods and cones will send a message to the bipolar cells in the retina, and then they're going to relay the message to the optic nerve, which is going to carry the messages to the central nervous system and that occipital lobe of our brain. So looking here at rods and cones, we can see that we have many more rods in green than we do cones in blue. And the light actually will pass through all the layers of the retina, hit that pigmented epithelium, and then come back. And then it will hit the rods and cones. And then we have the bipolar cells followed by the optic nerve cells. The photoreceptors, or our light receiving cells, are known again as rods and cones. Rods do not distinguish colors, so only different degrees of black and white, so we can see shades if something's dark or light, or if it's moving. And so our rods detect a lot of movement in our periphery. And they're spread out throughout the retina, but they're concentrated in the outside edges, again allowing us to have really nice peripheral vision. Cones, again, starts with C, so it helps us determine the color, which also starts with C, of different objects. It requires intense light to be stimulated, which is why in dim light we often can't see the color of kind of dimly colored objects. We might still be able to see like that blaze orange that people use for hunting, but not more toned down colors. To focus on an object, we have to move our eye around, so we get that light to focus right on the fovea centralis. It gets a sharp image, and this is what we do for reading. And this is where the cones are packed most densely. So here's another picture of the inside of the retina. We can see where the light rays come in. They'll bounce off that pigmented epithelium towards the rods and cones, where information will be gathered into the bipolar cells. Now here we can see that each cone in green has its own bipolar cell, so that they get stimulated much more easily. But those cones, it's about 4 or 5 little red cones to one bipolar cell in the retina, meaning we need a little bit more stimulation to help get that message passed along. So there are 3 different types of cones. Each is responsible for a different wavelength of light, blue, green, or red, and then combinations of these allows us to see different color. And some people lack a particular type of cone, usually the red and green, which leads to color blindness. So men are much more likely to be colorblind than women, but women occasionally can be colorblind as well. And this is typically determined at one of your first eye doctor appointments when you are asked to identify the different numbers that are in these circles, because some people that are colorblind can identify some of them, but not all. And people who are not colorblind typically can identify all of them. Now, if you're at your eye doctor and there's 1 or 2 circles that you can't identify, sometimes they'll put in a pattern that people who are colorblind can see the number, but people who have typical vision cannot see the number, so it's nothing to be concerned about if you're at the eye doctor and there's like all of a sudden one you can't see. So if somebody's colorblind, even other colors might seem a little bit different because they don't have that same mixing of colors that we would see in our typical eye. And I've always wondered, even like I see things and I call them red, but I might not see the same red that somebody else sees, but we all call it red because that was the color on the crayon and the crayon said red, or our teacher held up or our parents held up and they said, this is a red truck, and we're like, oh, okay, that thing is called red, and we might not all see the same color, which makes it absolutely one of the most interesting things is different types of perception. Now, I mentioned at the beginning there is a tribe in Africa, and they don't differentiate between green and blue in their language. And so when you give them a test to identify a blue square amongst other green squares, they really, really struggle with it. But they do differentiate between two different types of green, and we would struggle to identify the odd color of green in that circle. But they're easily able to point it out, and they laugh like, this is such a silly test. I can't believe you're asking us to do this. So language is also very important in color identification. So when we look at the chemistry of vision, so how vision works, we have about 160 million rods surrounding our cones and our eyes. And the rods contain a light-sensitive pigment called rhodopsin. And the cones contain a similar pigment, but it's less sensitive to light. And rhodopsin contains a form of vitamin A. And this is why people say, well, eat your carrots and then you'll be good at seeing, because carrots also contain vitamin A. So when a single photon of light strikes a rhodopsin molecule, it divides into two compounds. Retina, a pigment portion, and opsin, the protein portion. And this division alters the cell membrane of the rods and produces that action potential. So again, it's going to let that sodium rush into the cell, the potassium will rush out, and the action potential will occur. So neurotransmitters are then going to be released from the end plates of the rods, and that nerve message is conducted across the synapse to the bipolar cells, and then the same will happen at the end of the bipolar cells to the optic nerve. So if you have a mass deficiency in vitamin A, this can cause damage to the rods. Luckily for us, we do get a lot of vitamin A in different foods that we eat. This is why you're supposed to eat all the different colors of the rainbow foods. Organ meats also have a lot of vitamin A for cultures who didn't live in a place where vegetables were readily available. So rhodopsin is extremely sensitive to light, but in bright light, it's broken down faster than it's restored. And the options used for color are much less sensitive, but they operate with greater light intensity. So rods are only active during available limited light intensity, which is why images appear in shades of gray. So that so in dusk and dawn, we're not great at seeing colors. So an after image is an image that appears blue or green lines, so like blue or green lines that stay in your vision after a camera flash has gone off. If you look at a bright light and then you look somewhere else and you can kind of still see the shape of the light in your eye. So we have a positive after image. So if we look into a light and then we close our eyes, and we have a negative after image when the lights are exposed to a bright colored light for long periods of time. And this is going to be our cells adapting to overstimulation. So they lose sensitivity and they're not able to kind of recover from that rhodopsin break.